this will be lecture 13. And over the next three lectures, we're going to cover what's called Thevenin and Norton models or circuits or equivalent circuits. I consider the Thevenin and Norton model as one of the main part that will be covered in your exam 1. And when I say one of the main parts, I look at it as having three substantial parts: nodal analysis, mesh analysis, and then you're going to cover Thevenin and Norton circuit. Now, very important are power calculations, knowing how to apply the passive sign conventions. Voltage and current division are a small part. So these things are add-on that are super important, essentially. But if you ask me what are the three major parts of your exam 1, and I would say nodal analysis, mesh analysis, and Thevenin and Norton circuits. Okay, so today we begin essentially one of 3 mini lectures on Thevenin and Norton models. And I want to give you, before I begin, I want to give you a feel for why do we need a model. Okay, beyond that, I'm doing it because it's, it's required in engineering 17. So I'm going to go to the document camera here and talk a little bit I want to give you a feel for why do we need models. Okay, so give me a second and hopefully the document camera will cooperate nicely, I would say today. Okay. Okay. Thank you. So let's assume that we have some complicated circuit that I'm putting as a box here. Okay, some complicated circuit. Okay, so let's assume that we have some complicated circuit in this box. And why complicated circuit? I mean, the circuit can have voltage sources, current sources, resistors for now, and later on we're going to add dependent voltage and dependent current source as well. Okay, we have a complicated circuit here, and the circuit connects to the outside world via these terminals I'm going to call A and B. So this can be any kind of large circuit. This is to give you a feel for why we need Thevenin and Norton, essentially Thevenin and Norton models. Right? So, and let's assume that I connect this to a resistor. I call it R, and I ask you to find the current through the resistor R, but I ask you to find that current for R equal 10 ohms, 20 ohms, 30 ohms, 40 ohms, 50 ohms, 60 ohms, up to 100 ohms. You can imagine what that would be given that you have a complex circuit that could be multi-node or multi-meshes. So you basically would have to do a nodal or mesh analysis as many times, as 10 times again that we have for the 10 value of the resistor, so that I can have the current in it. So in many respects, sometimes having a model, an accurate, meaning exact, not an approximate model for this complicated circuit, and if the model is actually simple, that we could essentially address this in a lot easier way, there's some really value in having models. Okay, and that's what we're going to see in that later. So models are really a major part of engineering discipline, engineering content, because it allows you to treat complicated circuit, complicated systems in a way that's a little bit simpler when we can come up with a model. Now, again, assuming that the model is an accurate model, not some sort of approximate, that doesn't work. So these particular issues here, we're going to talk about circuits that have two terminals. This is what I call one port. Okay. So two terminals, in essence, you can connect one element to it via these two terminals. So these are the circuits that we're concerned about, and we're going to learn to develop two separate models. One is the Thevenin model, and the other one is the Norton model. So that's our focus over the next 3 mini lectures here, which constitute a significant part of your exam number 1. So I'm going to stop here and go to the PowerPoint and continue there. So let's go to the PowerPoint here and do a little bit more generic introduction. So again, we're looking at today Thevenin and Norton models, Thevenin and Norton circuits, Thevenin and Norton equivalent circuits for what's called one-port network. And one-port network, again, our network that connects to the outside world via a pair of terminals. Here I'm going to call them A and B. The outside world can be a simple load like a resistor. It can also be another circuit. But what we're looking at in this particular section here is to create a model for network A. So having simple model, again, will show to be very useful when we're dealing with complicated circuits. So sometime actually creating that model can be done experimentally, or obviously in this class, we're not doing any experiment. You're going to be doing it using mesh and nodal. So I'm going to show you the step to create the model, and they're going to be two models. One is called Thevenin model. The other one is called Norton. So the important parameter in terms of that load on the right, think about, for example, your stereo system, and then you have a two-line that connects to your speaker. Does your speaker care how that signal that's coming down the lines is created? What essentially your speaker cares about is the voltage and current. Your speaker cares about the voltage and current that's coming down that line to create the sound that it needs to create, okay? So clearly the load here in this particular case, what it cares about is a particular voltage across it and a particular current that's coming through it. That's the important parameter here that we have. So again, the formal thing, we're going to say given network A and B, they're connected at two terminals. The only restrictions here is what I have in orange here. If you have a dependent source in network A, it cannot be controlled by a voltage or current in network B or vice versa. Okay, so network A and B are fairly independent of each other, essentially. That's the only restriction. I'm not going to give you something like that, obviously, in this course, but I just want to make sure that I have a complete set of information for you here. All right, so here is the Thevenin model. So network A can be modeled exactly by a simple circuit, which is an independent voltage source in series with a resistance. A resistor, okay? We're going to call the voltage source, the independent voltage source value VOC. You're going to see why we're calling it VOC. VOC will stand for V, open circuit voltage, okay? And it is in series with, we're going to call it the Thevenin resistance, all right? So this is the Thevenin model for literally any complicated circuit. What I'm hoping you notice is that this Thevenin model is the practical source model that we saw about a lecture ago when we talked about what's a practical voltage source model. We say the practical voltage source model is an independent ideal voltage source in series with a source resistance. Well, that's what the Thevenin model is. It's a practical source model. The independent voltage source, we're going to call its value VOC because we're going to find out how to find VOC. And the resistance is a Thevenin resistance RTH. So when I ask you, so what's coming to you this lecture and the next two lectures, you're going to be given a circuit and you're going to be asked, find or calculate or determine the Thevenin equivalent model or the Thevenin equivalent circuit for that circuit. And when you ask that questions, you essentially being asked three things. You're being asked to give the model, which is what I'm showing you right now. So if you are asked for a Thevenin model, the first thing you do is to draw the model, which is a very simple. The independent voltage source in series with the Thevenin resistance. The voltage source value is VOC. Okay, and then the next two steps is to calculate VOC and calculate the Thevenin resistance. So these are the three things that will be implied when you ask a problem, give the Thevenin model about a particular circuit. Okay, so we're going to practice this, but first we're going to learn how to find VOC and how do we find the Thevenin resistance. So again, this is the original circuits we have, that complicated circuit we call network A. And we want to model it given this simple practical voltage source model that we call the Thevenin model. All right. So we found VOC by simply looking at the open circuit voltage across A and B. So VOC is the open circuit voltage across the circuit you want to model without the load being present. Okay. So this is network A is what you want to do a model for. You simply find the open circuit voltage across A and B. And we are going to be doing so using mesh or nodal analysis. So this is why we spend so much time developing proficiency and skill in mesh and nodal, because right now you're going to see I'm overlaying Thevenin circuit, Thevenin model. But once you look at the model and you need to find VOC, you go back to doing you go back to doing a nodal or mesh analysis approach to the problem here. So VOC is the open circuit voltage across terminal A and B with no load being present, for essentially just for the circuit being modeled. Okay, that's what VOC is. All right. Of course, we're going to do several examples for you to see how that play out. The Thevenin resistance is the equivalent resistance looking in. That's what you're seeing me putting that arrow here. It's the equivalent resistance looking in when all of the independent sources are turned off. So it's like unplugging the circuit and measuring the resistance looking into terminal A and B. All right. So notice that the model has nothing to do with the load on network B, and it shouldn't, because the model is for network A, nothing to do with that. All right. So the Thevenin resistance, we turn off all independent voltage and current source. And of course, you're going to need to know what happened to a voltage source when you turn it off. So if you forgot what we talked about turning off, when we did that in superposition, if you turn off a voltage source, it can be represented by a short circuit, a wire, because you want it to be 0 volt. If you turn off a current source, you want the current to be 0, and we represent that by broken wires, by an open circuit. Okay, so we're going to turn off all independent sources and look at the equivalent resistance looking into terminal A and B. Notice we do not touch the dependent source. Dependent source never got turned off. Okay, so these are the two steps into the Thevenin model. First, we have to come up with the model. That's right here. You have to show me you know what the model is. Then you proceed to calculate VOC from the given circuit, which is essentially the open circuit voltage across the circuit you want to model. And then, so when we calculate VOC, nothing is turned off. It's the original circuit. Okay, and we're finding the voltage across terminal A and B. And then when we calculate the Thevenin resistance, we turn off all independent sources. We now know that independent voltage sources turned off become a wire. Independent current source turned off become an open circuit. And we calculate the equivalent resistance looking into A and B. Okay. So this is essentially the steps in finding the Thevenin model. We're going to essentially apply this to see how that works. Of course, we start with simple circuit, and we increase the complexity of the circuit. So this circuit is saying, find the Thevenin equivalent circuit to the network to the left of terminal A and B. So in essence, I'm looking for a model for everything in the box here that I have, everything here in my box. Okay. So the only thing that should not be included in the model is the load, which we don't even know what the load is, but we want the model to take care of everything to the left of A and B. Okay. So again, when we are asked for a model, you need to first produce the model and then find VOC and RTH for the circuit. So I'm going to show you the model at the end, but the two steps in the process, the two calculation steps are finding VOC, and then after that, finding RTH. Okay, so you're going to start seeing that I'm doing simple circuit, and you're going to see a little bit increasingly more complicated, particularly in lecture 3. So the first cut, we're just going to look at some simpler circuit that we can easily find the Thevenin resistance for. All right. So finding VOC is essentially the original circuit I want to model, and I'm finding the open circuit voltage. And then at this point, this is where you get to decide, if I don't specify a method, you get to decide whether you want to use nodal or mesh analysis on the circuit. Okay. But in essence, I just want to find the voltage across A and B here. All right. So I'm going to be doing nodal analysis. I could have easily done mesh. There's nothing really that drastic about either nodal or mesh here. It's pretty simple. Okay. So this is my nodal setup. I put my reference node at the bottom. Okay. So that means I have two nodes, V1 and V2. You'll notice I don't have a node on VA. I'm sorry, I don't have a node at terminal A because there is no current on the 3 ohm. It's just open. So there's no current. So essentially there is no voltage drop on the 3 ohm because there's no current. Okay. So I have two nodes beside the reference node. And of course, the first thing I'm going to do is write a source equation for the 3 volt. As you know, when we're doing nodal analysis, we form super node about the voltage source, which I did. That super node has the reference node. So I'm not going to do a KCL about it, but we write one source equation per voltage source. In this case, V1 equal to 3 volt. The next thing I'm going to do is write a KCL at node V2 to give me my second equation. And that KCL is going to be I1 plus 6 equal I2. Again, realize there is no current under 3 ohm because it's just hanging, so the current is 0. Okay, so we have I1 plus 6 minus I2 equals 0. Okay. The rest is typical Ohm's law. Put under this case, the one KCL equation and solve for V2. We already really have V1. So Ohm's law, I1, passive sign convention, V1 minus V2 divided by 1, and then I2 is V2 divided by 2. I bring these two things into the one KCL that I have, the KCL at V2. I'm going to solve for V2, and I get V2 equals 6 volt. Okay. And you can show that V2 is actually equal to VOC because there is no voltage drop across the 3 ohm because it has no current. If a resistor has no current, it has no voltage by virtue of Ohm's law. So the voltage VOC is actually V2. So VOC is V2 in this particular case. Okay. So I hope that makes sense. I mean, obviously, we're going to need to do some practice to see different problem here. Okay. But my goal today is to give you an introduction, a couple of problems perhaps under your belt, and then we're going to keep picking it up. So now we're going to find the Thevenin resistance. So you see my crosshair, that's to imply turning off. And you're going to need to remember what happened when you turn off a voltage source, what happened when you turn off a current source. That's going to be very important to know. So when you turn off that 3 volt, that 3 volt is going to be replaced by just a wire. When you turn off that 6 amp current source, it's going to be replaced by broken wire. Okay. So what we have, and then we're looking at the equivalent resistance, this is what we have. This is where the current source was, that X. This is where the voltage source was, that line. Okay. This particular simple circuit, I can simply, looking at the resistance looking in, I can see that the 1 ohm and the 2 ohms are in parallel, okay? And the result in series with the 3 ohm. So this particular case, the 3 ohm had no impact on VOC, but it does on the Thevenin resistance. So this is a case where, again, the Thevenin resistance, I put the 1 and the 2 ohm in parallel, and the result is in series with the 3 ohms. So we get the Thevenin resistance being 3.66. And finally, this is your model, your Thevenin model, which is an exact model, by the way. Okay. The Thevenin model is VOC being 6 volt in series with the Thevenin resistance being 3.66. I hope this gives you a pretty good introduction of what the Thevenin model is. I want to do a second problem just to give you a little bit of a different feel for the solution. But this actually provides you the essence of the Thevenin model for circuits. So let's look at example 2. Example 2 is kind of, it's kind of reach out a little bit why we need model. So what we did in example 1, we essentially just found the model, okay? So it's just like find the model. Example 2 gives you a little bit of a purpose here. That's why I like example 2. It says, okay, I have this circuit that have a resistor R, okay? I want to know what is the value of the resistor R that would maximize the power that dissipates in the resistor R. All right, I want to find that out. So I'm going to go back. You perhaps maybe have forgotten already maximum power transfer. So I'm going to go back to something we did a couple lectures ago. Let me just share that with you here. Hang on a second. Okay. A little bit of a recall. Okay, so a little bit of a recall from maximum power transfer lecture. So remember, essentially, we introduce practical voltage source model. And the practical voltage source model was this. Okay. And of course, we now can relate that this is actually similar to the Thevenin model, which is VOC and the Thevenin resistance. Okay. So the Thevenin model is actually a practical source model, and we now know how to calculate VOC and RTH. So now what happened essentially, if we plug a particular resistor, say RL, say R, and I ask what value and we ask what value of the resistor R would maximize its power. And what we found out when we did the mini lecture on maximum power transfer, that value is R equal RTH. Okay, this resistance will be the same value, will maximize the power dissipated in that resistor R. So when you are being asked that question, so we're going to first determine the Thevenin resistance for the circuit. Then we're going to make essentially the resistor R the Thevenin resistance and find the power that's essentially the maximum power, having adjusted the resistor so that it is the Thevenin resistance. Just a little bit of a recap from the maximum power discussion and lecture that we have. So let's go back. Let's go back to the PowerPoint here. And that's what this is saying. Find the value of R that maximizes the power dissipated in R. So what I'm going to do, I'm going to put my A and B here. I'm going to say A is here, and then B is down there. Okay. So I'm going to create a Thevenin model for everything except the resistor R. And once I'm done with the model, I'm going to set that resistor R value to RTH, and then I'm going to find the power dissipated by R. So that's basically the process I'm doing here. So first step here, again, just a little bit of a recall. If you remember that the Thevenin model is a practical source model, just like I was trying to infer here in the document camera. And when those two resistors are the same, the load dissipates the maximum power. That's the best you could do. The best you could do is to send half of the power to an external load. Okay. All right. So we're going to, again, eventually, when we get the Thevenin resistance, we're going to set up the resistor to the Thevenin resistance and then find its power. So first thing is to find the Thevenin model for the circuit without the resistor R. Okay, so you see me looking to find VOC, and then I'm going to find RTH. And in this particular case, I'm essentially doing mesh analysis. There are two mesh currents because this is not a finite mesh because of the open circuit here. That means the current in that mesh is 0. Can be current because there is no current from A to B. Okay, so that's why you don't see a current on that loop, if you will, on the bottom right. So you have two mesh current, mesh I1, mesh I2. Okay. And then I put voltages on my resistors that don't have voltages. I don't need to put a voltage on the 4 ohms because it has no current. There's no place for the current to go, so there is no voltage across it. I could put a voltage, but it won't make any difference. Okay, so this is the case here where we have one current source on the perimeter belonging to one mesh. So we write the source equation for that current source. I1 is minus 2 amp because the way I define I1 is going this way, opposing the 2 amp source. So I1 is minus 2 amp. All I'm going to do is a KVL in mesh I2. So minus 6 minus V3 or plus 6 plus V3 equal to 0. Then I go ahead and write Ohm's law for V3. So V3 is minus 3I2 because, again, there is no mesh current in that bottom loop. Okay. And I use that in the Ohm's law equations and then I calculate I2 to be 2 amps. Okay. So I have I1 and I2. I can essentially find VOC. VOC minus VOC minus V3 plus V2 equals 0. Of course, I forget to mention that the 5 ohm down there also has no current because it's just hanging, basically. So we find that VOC is equal to 2 volt. Okay. It's a simple circuit to solve, but nevertheless, it shows the examples as well. Okay. So now that I have VOC for the circuit, now we're going to go back and find the Thevenin resistance. You see me using that crosshair. This is to imply to you again, you need to turn off these independent voltage and current sources. So you need to know what happened when to a voltage source when you turn it off, what happened to a current source when you turn it off. Okay. So the 6 volt is going to become a short circuit, and the 2 amp is going to become an open circuit. So you get this. Okay. So that open circuit here essentially disabled the 1 ohm because that makes the 1 ohm has no current. That short circuit here, short circuit the 3 ohms, forcing its voltage to be 0. So the Thevenin resistance looking into A and B is essentially the 4 ohm in series to the 2 ohm and the 5 ohm. The 3 ohms and the 1 ohm have no effect on the circuit, basically. Okay, so we have the Thevenin resistance to be 11 ohms. Okay, again, let me say again here, the 1 ohm, because of that open circuit here created by the current source that was there, that forced the 1 ohm to have no current on it because there is no place for the current to go. So the 1 ohm is just hanging. The 3 ohm, on the other hand, is essentially as a parallel short. If you think about the parallel short as 0 resistance, so you have 0 resistance here. If you try to put 0 ohms in parallel with the 3 ohms, you're going to find that the equivalent resistance is 0. Okay, so it short circuit the 3 volt, I'm sorry, the 3 ohms. It forces the voltage on the 3 ohm to be 0. So the current on the 3 ohm is also 0. So the 3 ohm and the 1 ohm have no impact. So the net resistance is the 4 ohm in series to the 2 and the 5. So we got 11. So again, this is the Thevenin model here. VOC is 2 volt. The Thevenin resistance is 11. And then now for maximum power transfer, we set R to 11 as well. Okay, and we can calculate the power that the 11 ohm R would see, and it's 0.091 watts. So this is actually a good indicator, actually, why models are important. We can answer maximum power questions. We can also solve the circuit for multiple values of a load, which would be very, very laborious to do if we didn't have that. So finally, I have a problem for you to do. And this problem essentially is asking you to find the Thevenin equivalent model for the circuit about the 50 ohm. That is the 50 ohm here that I'm pointing out with the red dots here. The 50 ohm is not part of the model. Okay. When you say finding about the 50 ohm, that is the 50 ohm is not in the model. So find the Thevenin equivalent circuit for that. And then calculate using the model the power dissipated in the 50 ohm. Okay. So using the model, connect the 50 ohm and calculate the power dissipated in the 50 ohm. And finally, if the 50 ohm were to be adjusted so that it dissipates maximum power, which is essentially setting the 50 ohm to the Thevenin resistance value, find what that maximum power would be. So this is the part again that I'm asking you. Let's focus right now on finding the Thevenin model or the circuit without the 50 ohm, and then we can answer the power question after. I'd like you to pause the circuit, to pause the video, to pause this or stop it, and then spend about 35 minutes on this. See if you can do. The first part of the problem is to calculate the Thevenin equivalent model about this terminal that I have here. So we could call him this A and the bottom B. So the 50 ohm is not part of the model. All right. Then use that model, the Thevenin model, to calculate the power dissipated in the 50 ohm. Okay. So that's question number 2. Question number 3, let's assume we change the 50 ohm so that it dissipates maximum power. I'm hoping now you know that making the 50 ohm equal to the Thevenin resistance. What would that maximum power be? Okay, so you have 3 questions, but for the first part, if you can get me the Thevenin model, I would be tremendously happy about that. So again, stop the video, spend about 35, maybe up to 40 minutes on this and see if you can answer these questions, and then you can restart the video. Okay, so we're looking at, again, finding the Thevenin model about the 50 ohm. The 50 ohm is not present. Second problem is to calculate the power, connect the 50 ohm, calculate the power dissipated in it. Third question is, let's change the 50 ohm so that it dissipates maximum power, setting it essentially to the Thevenin resistance. What is that power? So the second part, again, is this part here. If the 50 ohm were to be adjusted so that it dissipates maximum power, what would that power be? Okay, so first part, again, I'm going to do a Thevenin model about everything here in my box except the 50 ohm. Okay, everything there. I want the model for this. And then I can address the question about the 50 ohm after that. So VOC, the Thevenin circuit, the Thevenin resistance, and then the model itself. All right. So here is VOC. VOC is simply the open circuit for the circuit that I'm modeling. Mesh, nodal, whatever you feel like it. Okay. You're going to see now, I'm assuming your mesh and nodal are understood, and you have some proficiency in mesh and nodal. Okay. So I'm using nodal here. Bottom node I'm putting as a reference node. So the top node here on the right is VOC, and then I have V1, V2, and VOC. So it's a 3-node problem. I get VOC right from the nodal approach right there. So the first thing I'm going to do here, I do have a super node, which I'm drawing here. Okay. Now the super node has the reference node, so I'm going to do nothing with it, but so we know here. And then I'm writing the I'm writing the source equation for the 10 volt, which is V1 minus 0 equal 10, so V1 equal 10. So I have I'm going to do two KCL equations, one at V2, one at VOC. So there is my KCL equation at V2 and at VOC. At V2, current coming in equal current coming out. I got I coming in, and I have I1 coming out, I2, and the 5M. At node VC, I have I2 and 5 coming in, and I have I3 leaving. So these are my two KCL equations, one at V2, one at VOC. I do Ohm's law, I put them in, and I'm going to solve for VOC, V2, I already have V1. So Ohm's law again, passive sign convention, I is V1 minus V2O divided by 10, I1 is V2 divided by 20, I2 is V2 minus VOC divided by 30, and I3 is VOC divided by 40. So I bring those things to my two KCL equations, and then I solve. I get my two equations to unknown. I'm assuming V1 is now known. And I really need VOC, but I solve for V2 and VOC. So VOC is 81.74 volt. Okay, this is a pretty standard nodal problem. Again, once you realize what you're seeking here, the method for solving it is what we've been doing for the last month. Okay, now I'm going to go back and find the Thevenin resistance here. And what I'm going to do, I'm going to essentially turn off this thing. That's why you see them somewhat of a dotted line. I'm going to turn off these things, and you're going to need to know what happened when you turn off a voltage source, what happened when you turn off a current source here. Okay, so when we do that, the current source becomes unopened, and the voltage source becomes a short. Okay. And then we're finding the equivalent resistance looking into A and B. So I can easily see that the 10 ohms and the 20 ohms are in parallel. Okay. The net result will be in series with the 30 ohms, and the net result in parallel with the 40. Okay. So that's what you got here. Again, 10 is in parallel with 20, and that combination is in series with the 30, and that combination is in parallel with the 40. So you get the Thevenin resistance to be 19.13. Okay. So the model essentially is the Thevenin model, VOC, the Thevenin resistance, and then I connect the 50 ohm right now, and then I can calculate the power that the 50 ohm dissipates by just finding the current. I find the current from the Thevenin model. Once I connect the 50 ohm, I get the current to be 1.18 amp, and then from that current, I can calculate the power in the 50 ohm resistor, which is 69.90. Okay. So the third question that you have, if I make the 50 ohm, if I change it so that it is maximum power, that would make the 50 ohm equal to the Thevenin resistance. That's what you see here. And then I can again calculate the current and then recalculate the maximum power then, and I find it to be 8732 watts. Okay. So this is a little bit showing you why we need model. All right. What I want you to focus right now is not necessarily that second and third question. It's essentially finding the Thevenin model. That's what I want the focus to be. We can answer other questions in a later time. Okay. So in this lecture, we've introduced the Thevenin model. We want to make sure you understand that the Thevenin model is the practical source model. So when you get a Thevenin model questions, you're essentially being asked for the model. Whether you give me the model at the front end or you give me the model at the back end, I'm good either way, but you're being asked for the model. And then you need to calculate VOC, which is the independent source value in the model, and the Thevenin resistance, RTH. Okay, so these are the process. And these cases that we did today in finding RTH, we essentially were able to combine resistance because the circuit was simple. Okay, we look at more complicated circuit in the future. But generally, to find VOC, you have to do either mesh or nodal. That's standard there, so we're going to need to essentially think that way. The next mini lecture, I'm going to introduce the Norton model, and then we're going to practice some more complicated problems. Thank you.